The greatest mystery about the universe isn't how it began. It's why it didn't end immediately. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. They should have erased each other completely, leaving behind nothing but light. No galaxy, no black holes, no Earth. No one to wonder where the universe came from. And yet, here you are. Tonight, we'll follow that contradiction back to the beginning of time itself. If this kind of slow, quiet science is something you love, a gentle like or a soft tap on subscribe means everything to me. It tells me that these little stories are finding the right people, and it keeps this whole quiet world alive. Now close your eyes if you'd like. Let's begin. Einstein's most famous equation hides a direction almost nobody says out loud. We read that energy equals mass times the speed of light squared, and we read it one way, mass becoming energy, the way a sliver of matter inside a reactor releases a flood of heat. The equation has no favorite direction. It runs just as honestly the other way. Pour enough energy into a small enough space, and that energy becomes mass. Light becomes matter. And in the opening moments of everything, it did, over and over, in both directions at the same time. To make matter out of light, you have to concentrate energy fiercely. Bring two photons together hard enough, with enough energy folded into the collision, and both can disappear. And where they were, you now find a particle of matter beside its exact opposite, a particle of antimatter. This is not a thought experiment we are guessing at. We do this in particle accelerators today, on purpose, turning light into matched pairs of matter and antimatter and back again. The catch is temperature. Collisions only carry that much energy when everything around them is savagely hot, and the early universe was hot in a way that is difficult to hold in the mind. Above roughly 6 billion degrees, ordinary light carried enough punch to keep manufacturing particles of matter out of nothing but its own energy. That temperature is about 400 times hotter than the core of the sun, the place where hydrogen is being crushed into helium right now, and the whole cosmos was sitting at that heat and hotter. So picture what that early universe was actually doing. Light was forever congealing into pairs of matter and antimatter, and those pairs were forever finding each other and annihilating back into light. A particle and its antiparticle cannot coexist quietly. Put them together, and they erase each other completely, converting all of their mass straight back into energy, back into photons, obeying the same equation in the direction we usually read it. Creation and destruction ran at the same rate, in perfect step, a two-way traffic so balanced that the number of matter particles barely changed from one instant to the next. We tend to imagine the beginning as an explosion of stuff. It was closer to a standoff, energy and matter trading places so evenly that neither side was winning. Now let the universe cool, because it was expanding, and expansion drains heat the way stretching a spring drains its tension. Once the temperature fell below that 6 billion degree line, light no longer had the energy to make new pairs. The forward direction of the equation quietly shut. But the backward direction stayed wide open. Matter and antimatter could still find each other, and when they did, they still annihilated, still poured themselves back into light. A door that only swings one way. Every particle of matter meeting its antiparticle and vanishing, with nothing left to replace it. Follow that logic all the way to its end, and it arrives somewhere clean and terrible, A universe that began in perfect balance does not cool into planets and people. It cools into pure light and nothing else. Light is not nothing. A cosmos flooded with radiation still holds every bit of the energy it started with, so in what sense is that empty? The answer is that light does not build. Two beams of light cross straight through each other and continue on, unchanged, indifferent. Photons do not stick together, do not settle into atoms, do not pull on one another and gather into clumps. A universe made only of light has energy pouring through every cubic inch of it and not a single thing anywhere inside it. No structure, no chemistry, no slow gravitational gathering that could ever become a star, a world, a body lying in the dark listening to this. Why is there structure rather than only light? The empty, light-only universe is not the strange outcome that needs explaining. It is the ordinary one. A perfectly balanced set of books, matter and antimatter in exactly equal amounts, annihilates itself down to radiation every single time. That is the default. That is what the equations hand you when nothing tips the scale. So the existence of the protons in your hand is not evidence that the universe was generous. It is evidence that somewhere in that furious back and forth, the books failed to balance. For every billion antiparticles, 1,000,000,001 particles of matter, and only that lonely surplus was left standing when the annihilation finished and the door swung shut for good. One extra part in a billion. If you filled a stadium with 200,000 people and asked matter and antimatter to pair off and leave, the stadium would empty out almost completely, and you would be left staring at a single person sitting alone in 100,000 rows of seats. Everything we have ever seen or measured or loved is built from that scale of leftover. The stars, the galaxies, the iron in your blood, the calcium holding you upright tonight. All of it is the residue of a war that matter won by the narrowest possible margin, and mostly lost. This is the first frozen imbalance in a chain of them, and it will not be the last. Each stage of this story turns on some perfect balance, failing by a hair, and each failure leaves behind exactly the piece of the universe we happen to be made of. We have assumed the universe was once hot enough to trade light for matter, hot enough that 6 billion degrees was a cool afternoon by comparison. We have assumed the past was not a fainter version of the present, but a radically different place, ruled by physics we cannot see operating anywhere around us now. Tonight, the universe is cold and dark and mostly empty, and photons drift through it without ever congealing into anything at all. None of what we just described is happening in this room. So before we chase that surviving billionth backward through everything it became, we have to answer the question underneath all of it. How could anyone possibly know the universe was ever hot enough for light itself to turn into the matter we are made of? Nearly every galaxy in the sky is moving away from us. Not drifting randomly, some toward, some away, the way you would expect if they were just milling around. Away, almost all of them, and the pattern in how fast they flee is the whole key. The farther a galaxy sits from us, the faster it recedes, and the relationship is clean and proportional. Double the distance, and you double the speed of retreat. A galaxy twice as far away runs from us twice as fast. A galaxy 10 times as far runs 10 times as fast, and this holds across the entire sky in every direction we look. If galaxies were simply flying through space like debris from some central blast, we would not see this tidy rule. We would see a mess. What produces a clean doubling is not galaxies moving through space. It is space itself expanding, carrying the galaxies along like markings on a rubber sheet being stretched from every side at once. Stretch the sheet evenly, and any 2 points move apart at a rate set by how far apart they already are. Points close together barely separate. Points far apart race away. That is exactly the pattern in the sky, and it tells us the space between galaxies is growing. Run that expansion backward, and the consequence is not subtle. If the space between everything is growing today, then yesterday everything was closer, and 1 billion years ago closer still. And far enough back, the galaxies were not galaxies at all, but a smooth, dense fog with no room between anything. And here the physics turns concrete, because squeezing matter into less space does something you have felt with your own hands. Push down hard on a bicycle pump with your thumb over the valve, and the barrel warms under your palm. Compress a gas and it heats. Let it expand and it cools. The early universe was gas under the most extreme compression imaginable, so running the clock backward does not just crowd everything together. It drives the temperature up, higher and higher, until you reach the same savage heat we traced before, hot enough for light to congeal into matter. All of this is governed by one relationship. It says that the rate at which the universe expands is tied directly to how much stuff is packed into it, how dense it is, and nothing else. More density, faster the pull of gravity trying to slow the expansion. Less density, gentler that pull. The expansion rate and the density are locked together in a single line of mathematics written 100 years ago and still carrying the whole story on its back. That equation has one more piece we are going to leave sealed tonight. A term sitting off to the side that does nothing you would notice for billions of years, and then quietly takes over the fate of everything. We will come back for it. For now, it is enough that density and expansion move together, because that is what lets us rewind the universe with confidence instead of guesswork. Maybe the rewind breaks somewhere. Maybe you cannot just run the movie backward 14 billion years and trust that the same physics held the whole way. One line of evidence, the expansion, could in principle be explained some other way. The first of those independent clues was a prediction before it was a discovery. If the universe really cooled down from a dense fireball, that original heat could not simply vanish. Energy does not disappear. It would still be here, stretched out and cooled by all the expansion since, a faint bath of radiation soaking every direction of the sky at once. That radiation was predicted on paper, and years later, 2 engineers found it by accident while trying to get rid of noise in an antenna. It sits at just under 3 degrees above absolute zero, 2.7 Kelvin, the coldest even glow in existence, and it arrives from everywhere with no source you can point to. A cooled-off fireball is the only thing that makes it. Nothing else in physics predicts a uniform bath of microwaves filling all of space at precisely that temperature. Then comes a third clue from an entirely different branch of physics, and it may be the most damning of all. Count up all the ordinary matter in the universe, and you find that about 1/4 of it by weight is helium, the same helium that fills a birthday balloon. For roughly every 12 hydrogen atoms, there is 1 helium atom, everywhere we look, in old stars and young ones and in gas clouds that have never made a star at all. That last part is the problem. Stars do fuse hydrogen into helium, but stars have not been running nearly long enough to have made this much of it, and the untouched gas clouds prove it because they are already full of helium without ever having lit a single star. The only place that quarter could have come from is a universe that was once hot and dense enough to run nuclear fusion everywhere at once for a few minutes before it cooled too far to continue. The expansion comes from measuring galaxy light. The radiation bath comes from a microwave antenna. The helium comes from nuclear physics, worked out in laboratories with no telescope involved. Three questions, asked by different people, using different tools, in different decades, and every one of them points backward to the same instant, a universe billions of times denser and millions of times hotter than anything around us tonight. Anyone alone, you might explain away. All three converging on a single number is not something you argue with. It is something you accept and then try to understand. The cold glow those engineers stumbled onto is still pouring through this room right now, through the walls, through you. Hundreds of millions of those ancient photons crossing your body every second. The cooled remnant of the fireball we have been describing. The furnace did not leave. It is all around us, faint and everywhere, 13.8 billion years chilled, but never gone. And yet the rewind that gave us all this has a breaking point, and honesty demands we find it. The equation lets us run the clock backward through the fireball, past the moment light made matter, deeper and hotter with every step, and for a long stretch it keeps returning clear answers. But it does not do this forever. Push it back far enough, into an interval so brief, it makes a single second look like the whole age of the cosmos, and the mathematics stops cooperating entirely. Not because the universe wasn't there. Because the two theories we would need to describe it flatly refuse to agree with each other. So the honest question is not how far back we can see. It is where, exactly, the rewind stops returning answers at all, and what it means that physics itself has an edge. The clock we have been running backward does not slowly lose focus the way an old photograph fades. It works and works and works, returning sharp answers at every step down through the fireball, and then at one specific reading it stops, all at once, the way a road can stop not by narrowing, but by ending at the edge of a cliff. That reading has a number. 10 million trillion trillion trillionths of a second after the beginning. Written out, that is a decimal point followed by 42 zeros and then a single digit, a slice of time so short that a single ordinary second contains more of these moments than the universe has counted seconds in all 14 billion years of its life, and not by a little, by a margin so wide the comparison itself starts to lose meaning. The question is why? Why should the mathematics run flawlessly for step after step and then refuse, exactly there? The reason is not that the universe went missing at that instant. It is that describing the universe at that instant would require two theories to work together, and those two theories cannot stand to be in the same room. We have two great descriptions of reality, and each one is stunningly accurate inside its own territory. One is general relativity, which handles the large and the heavy, gravity written as the smooth bending of space and time, the thing that curves a planet's path around a star and keeps you pressed into your bed tonight. The other is quantum mechanics, which handles the tiny and the light, the jittery, uncertain behavior of individual particles that never sit quite still and never have one definite value for everything at once. In everyday life, these two never argue, because they govern opposite extremes. The heavy things are big, the quantum things are small, and their domains do not overlap. A star is never small enough to be uncertain. An electron is never heavy enough to bend space you could notice. Now run the rewind back toward that wall and watch what breaks. The entire universe, everything that would become every galaxy, gets squeezed into a region smaller than a single atom. And in that instant, the universe is both things at once. It holds all the mass and energy of a cosmos, so gravity and the curving of space matter enormously, and it is smaller than anything quantum mechanics has ever described, so the jitter and the uncertainty matter enormously too. For the first and only time, the heavy and the tiny are the same object. You cannot use one theory and ignore the other. You need both, speaking together, and when you force them to, they hand you contradictions instead of answers. 3 numbers sit at the foundation of physics. The speed of light, which sets the rules for relativity. The strength of gravity, which sets how much mass bends space. And a tiny number that sets the graininess of the quantum world, how much uncertainty is stitched into everything small. Take those 3 and combine them, and there is exactly one way to fold them together that produces a length, and exactly one way to produce a span of time. No adjusting, no choosing. The constants themselves pick the scale where all 3 regimes collide, and that scale is the wall. The time it names is that 42.0 instant. The length it names is smaller than a proton by as much as a proton is smaller than a city block. What actually goes wrong at that scale is stranger than a simple breakdown. The uncertainty built into quantum mechanics says that the smaller a region you look at, the more wildly its energy fluctuates, borrowing and repaying energy from moment to moment. Ordinarily, this is harmless, far too small to notice, but shrink down to that Planck length, and the energy flickering in and out of even the emptiest speck becomes so large that, by the first theory, that energy bends space around itself. The very geometry that relativity treats as a smooth, dependable stage begins to churn and pucker and tear, roiling differently from one instant to the next. Space and time stop being a stage at all and become something closer to a boiling froth, a foam with no fixed distances and no reliable before and after. Try to lay a ruler across it, and the ruler's own smallest markings blur by the entire length of the ruler. There is nothing left to measure with, because the thing doing the measuring is dissolving into the thing being measured. Is this not simply the beginning? The single point of infinite density where everything started, the true zero of the clock. The equations do seem to point there. Run relativity alone backward, and it insists on a moment of infinite density and zero size, a singularity. But a theory that returns infinity is not revealing a fact about the world. It is confessing its own failure. Infinity is the sound a theory makes when it has been pushed past the edge of where it works, the mathematical equivalent of a needle pinning at the top of a dial that simply cannot read any higher. The singularity is not a place the universe went. It is the marker showing us where our description gives out. We do not know that there was a moment of infinite density. We do not know that time had a starting line at all. The truthful statement is smaller and stranger than a beginning. Beyond that wall, we do not have a theory that works, so we cannot say what the universe was doing, or whether the word doing even applies, or whether asking what came before is like asking what lies north of the North Pole, a question built from words that stop meaning anything past a certain point. Not a mystery we have failed to solve. A place where the questions themselves have not yet been shown to make sense. The wall is not the edge of the story. It is the edge of one chapter, the earliest one, and everything on this side of it we can trace with the same confidence that let us rewind the fireball in the first place. Step just forward of that instant, out of the foam and into a universe our theories can describe again. And physics has something waiting that is almost as disorienting as the wall behind it. The 4 forces that shape everything now, gravity, and the 2 that rule inside the atom, and the 1 that lights your room, were not yet 4 separate things. So the question that pulls us forward is simple to ask and strange to answer. How does one force become 4, and what has to happen to the universe for them to come apart? 4 forces run everything you have ever watched happen. Gravity holds you to the bed and holds the moon to its orbit. Electromagnetism lights the room and binds every atom in your body together, and 2 more work only inside the nucleus, at ranges smaller than an atom, one gluing the core of matter together and one quietly taking it apart in radioactive decay. Four forces, wildly different in strength and reach. Gravity is so feeble that a child's magnet lifts a paperclip straight off the floor, beating the pull of the entire Earth. They feel like four separate facts about the world, four unrelated rules the universe happens to run on. They are not. The claim on the table tonight is that some of them were once a single thing, and that the number of forces in the universe depends on how hot it is. To see how a force could hide inside another, you have to know what sets a force's strength, and the honest answer is that it is not fixed. How strongly two particles push or pull on each other changes with how hard they slam together, which is to say, with energy. And energy, in a crowd of particles, is just another word for temperature. Heat is nothing more than particles moving fast and hitting hard. Hotter means faster, means more violent collisions, and there is a clean relationship, a simple line that converts a temperature straight into the energy each collision carries. This is the thermometer we will use for the rest of the night. Name a temperature, and it tells you the energy on the table. Name the energy, and it tells you which forces can still tell themselves apart. Because here is what changes when you turn that energy up. Measure the strength of the forces at the gentle energies of everyday life, and they sit far apart, three very different numbers, three forces of three different strengths. But their strengths are not frozen. Each one drifts as you climb in energy, some growing, some shrinking, and physicists have measured that drift directly in accelerators, watched the numbers slide as the collisions grew fiercer. Extend those measured slopes upward, higher than any machine can currently reach, and the three lines bend toward one another, and at a staggering energy, they very nearly meet at a single point. Three separate forces, three separate strengths, converging toward one shared value. At that energy, the distinction between them would wash out. They would no longer be three forces at all. They would be one. That convergence is not idle speculation, because we have already watched it happen once, all the way through, with two of the forces. Electromagnetism and the weak nuclear force, the one behind certain radioactive decay, look nothing alike at room temperature. One reaches across the room and lights it. The other cannot reach beyond the width of a nucleus. One is familiar, the other so short-ranged you would never guess it exists. And yet the mathematics said that above a high enough energy they are the same force wearing two masks. And when accelerators were finally built powerful enough to reach that energy, the two forces merged exactly as predicted. This is measured, repeated, real. Above roughly 1,000 trillion degrees, electromagnetism and the weak force stop being two things and become one, which we now call the electroweak force. Cool back down below that temperature, and the single force splits into the mismatched pair we live with. So one merger is established fact, witnessed in a laboratory. And that changes the character of the larger claim entirely. Once you have seen two forces that look completely different turn out to be one thing at high enough energy, it stops being wild to ask whether the pattern keeps going. If two became one at 1,000 trillion degrees, do all of them become one if you climb high enough? That is the idea called grand unification, and the temperature it points to is where those three drifting lines converge. A heat so far beyond the electroweak merger that the merger we can reach looks cool by comparison. The electroweak merger, we have seen. Grand unification, we have not. No machine we can build, and possibly no machine that could ever be built on Earth, can reach the energy where all three lines meet. To make collisions that hot, You would need an accelerator not the size of a city, but the size of a solar system, maybe larger. The energy sits about 1 trillion times beyond what our most powerful machines produce. So when we say the forces unify, we are standing on two very different kinds of footing. One is a measurement. The other is a line drawn upward from measurements, trusted because it has been right before, but not confirmed. The convergence of the three lines is suggestive, almost seductively neat, and it might be exactly true. It might also be that the lines nearly meet but miss, and that near miss would itself be telling us something about forces or particles we have not discovered yet. Some versions of grand unification make a testable prediction that the proton, which we treat as eternal, should very rarely fall apart, decaying over a span so long it dwarfs the age of the universe many times over. People have built vast tanks of water deep underground and watched enormous numbers of protons for years, waiting for even one to break. So far, not one has. That silence has already ruled out the simplest versions of the idea, which is science working exactly as it should, an elegant theory forced to answer to a patient experiment. As you climb in temperature, forces merge. As you cool, they split apart, one by one, each splitting locked to a particular temperature. Run that forward from the earliest instant we can describe, just past the wall, and the universe cools through a descending sequence of these splits, shedding a unified force at each threshold the way a falling temperature crosses one marked line after another. Whether the very top of that sequence is a single grand force or something we have not yet imagined, the lower rungs are solid. The electroweak split is measured. The universe really did have fewer forces when it was hotter. But naming the temperatures where forces split leaves the deepest question untouched. A temperature is only a number. It does not explain the mechanism. What actually happens to a single unified force to make it break into two forces of wildly different strength and reach? Cooling does not sound like it should shatter anything. Things get sluggish as they cool. They do not usually split into pieces that behave by different rules. And yet, there is a completely ordinary process, one happening in the freezer in your kitchen tonight, that does exactly this, that takes something uniform and, purely by cooling, forces it to pick sides and lose a symmetry it used to have. Understand that, and you understand how a force comes apart. Water is more symmetrical than ice, and almost nobody notices. A snowflake looks like the orderly thing and a glass of water looks like the formless thing, so we assume the ice is the one with structure. But think about what symmetry actually means. It means sameness in every direction, no direction any different from the rest. Liquid water has exactly that. Stand anywhere inside it and look any way you like, up, sideways, at any angle at all, and it is identical. Molecules tumbling past with no preferred direction anywhere. That is perfect directional symmetry. Now freeze it, and that sameness is destroyed. The molecules lock into a crystal, a rigid lattice with axes and angles, rows running one way and not another. Suddenly, direction matters. There are special directions along the crystal and ordinary directions across it, and the two are no longer the same. The water did not gain symmetry when it froze, it lost it. The high-temperature state, the liquid, was the symmetric one, and cooling shattered that symmetry into something rigid and directional and full of structure. We picture cooling as calming down, settling, becoming more uniform, and here it does the opposite. It takes a thing that was the same in all directions and forces it to choose. And it does not choose gently. There is a sharp line. 32 degrees on the household scale, and above it the liquid holds its perfect symmetry no matter how much you cool it, and the instant you cross below, the whole thing snaps into the rigid state. Not gradually. A threshold, with symmetry on one side and broken symmetry on the other, and no in-between. That snapping across a line is the thing physicists mean by a phase transition, and its deepest feature is the one we just watched. A system that was symmetric at high temperature is forced, by cooling past a threshold, to pick a configuration and lose that symmetry. And the crucial part, the part that carries over to the early universe, is this. When the crystal forms, every direction was equally available beforehand, and yet one particular arrangement gets locked in. Nothing chose it in advance. The symmetry breaks one specific way, out of all the ways it could have, and once it does, that choice is frozen into the structure. The system commits to an answer it did not have to commit to, and afterward cannot easily undo. Trust your own sense that this is odd, because that instinct is pointing straight at the mechanism the universe used. The forces of nature are tied to symmetries too, deeper and less visible than directions in a crystal, but symmetries all the same, describing which particles can turn into which and how strongly they interact. While the universe was hot enough, those symmetries held perfectly, and holding a symmetry is exactly what it means for forces to be unified, for particles that look different now to be interchangeable then. As the universe cooled and crossed one of its own thresholds, a symmetry broke, the same way the liquid's symmetry broke at its freezing line. And when it broke, a single unified force committed to one configuration and came out the other side as two forces of different strength and reach, the way one symmetric liquid came out as a crystal with special directions where before there were none. This is not a loose comparison poured over the physics to make it feel familiar. It is the same mathematics, the equations physicists use to describe water freezing and the equations they use to describe forces separating share the same skeleton, the same idea of a symmetric high-temperature state giving way to a broken low-temperature one at a critical threshold. When they wanted to understand how the electroweak force split into electromagnetism and the weak force, they reached for the physics of freezing, because it was already the right tool. The universe cooling through its force-splitting thresholds is doing, at the level of its deepest laws, what the tray of water in your freezer is doing right now while you lie here. Freezing releases energy. This sounds wrong at first, since freezing is what happens when you take energy away. But the water itself gives some back, at the moment it locks into a crystal, dumping a burst of heat as it settles into the lower energy arrangement. That released warmth has a name, latent heat, and it is why a lake takes so brutally long to freeze solid, even after the air has gone far below freezing. The water keeps handing back heat as it crystallizes, fighting the cold with warmth pulled from its own change of state. The lower energy state sits below the symmetric one like the bottom of a hill sits below the top, and dropping from the high state to the low one, the transition releases the difference. Hold on to that hill, because it hides a trap. A ball at the top of a hill will roll down to the bottom, to the low energy state, given the smallest push. But sometimes a system gets stuck. It cools past the point where it should transition, past the threshold, and yet it does not fall, held in the high energy state longer than it has any right to be. You have likely done this by accident, with a bottle of very clean water chilled below freezing, still liquid, still symmetric, sitting there in a state it should have abandoned, until one tap sends the whole thing crystallizing at once. Supercooling. A system marooned in the symmetric state after the moment it was supposed to leave. Now put those two ideas together, the stuck high-energy state and the burst of energy waiting to be released, and aim them at the whole universe. Suppose the early cosmos, cooling through one of its earliest thresholds, did not fall to its low-energy state on schedule. Suppose it hung there, supercooled, marooned in a symmetric high-energy state it should already have left, its latent energy still locked up, unreleased, waiting. A tray of water doing this just sits quietly on the shelf until it tips. But the energy stuck inside the universe was not sitting in a tray. It was filling space itself, and space, unlike a shelf, answers to gravity. What does a whole universe do when it gets trapped in a high-energy state it cannot escape, with all that energy pressing outward on the fabric of space and nowhere yet to go? Energy trapped in space does not just sit there. A supercooled tray of water on your counter holds its locked-up energy quietly, waiting to be tipped, and nothing about the room changes while it waits. But the early universe had that same locked-up energy spread through the fabric of space itself, and space answers to gravity, and gravity responds to energy no matter where it hides. So the question is not whether the trapped energy does something. It is what a region of space does when it is filled, everywhere, with energy that cannot yet be released. Ordinary stuff, matter and light, thins out as space grows. Spread the same gas through a bigger box, and each corner holds less. The trapped energy of a stuck symmetric state does not behave this way at all. It is a property of empty space itself. So when that space expands, you simply have more empty space, each cubic inch of it holding the very same energy as before. The energy does not dilute, it multiplies with the volume. Grow the region, and its total trapped energy grows right alongside it, refilling every new pocket of space at full strength. That single fact rewrites how gravity behaves. Gravity from ordinary matter pulls inward, always, slowing any expansion down. But energy that refuses to dilute exerts a kind of pressure that points the other way, a pressure that pushes space to expand rather than resisting it, and the more it expands, the more of this pushing energy there is. You can feel the runaway building. Expansion creates more space. More space holds more trapped energy. More energy drives faster expansion, which creates still more space. Each doubling feeds the next. When a quantity feeds its own growth like that, it does not increase steadily. It explodes in a very specific mathematical shape. The size of the region doubles, and then in the same span of time doubles again and again, each doubling taking the same tiny interval as the last. This is the same runaway math behind a rumor that spreads by each person telling two others, or a savings balance, where the interest itself earns interest. 2 becomes 4 becomes 8 becomes 16, and the totals stay modest for the first few steps and then erupt past all intuition. A page folded in half 50 times, if you could actually do it, would reach past the moon. That is what repeated doubling does. Now apply that to the universe. In an interval so brief, it makes the 42-0 instant we met at the wall look almost long. The trapped region doubled in size not once or twice, but around 60 times over. 60 doublings takes a patch of space and multiplies its size by a factor with 26 zeros after it. To carry that in the body, imagine something the size of a single proton, already unthinkably small, blown up in that flick of time to the size of a grapefruit you could hold in one hand. A proton to a grapefruit is a leap of exactly that scale, and the proton in this picture was not a proton. It was the entire region that would become everything we can now see. Nothing travels faster than light. That is bedrock. So how can space blow up by 26 zeros in an instant without shattering the one rule physics never breaks? The resolution is precise, and it matters. The speed limit governs things moving through space, a particle chasing another particle, a signal crossing a gap. It says nothing about how fast space itself may stretch. No object during this expansion outran a beam of light in a race between them. The objects were barely moving through space at all. It was the space between them that was ballooning, carrying them apart faster than light could bridge the widening gap, without anything ever winning a foot race. The rule stays intact. It simply never applied to the stage, only to the actors on it. While that region ballooned, it was not perfectly smooth, and it could not have been. The quantum world forbids perfect stillness. Even the emptiest patch of space flickers with tiny fluctuations, energy trembling faintly up and down, never quite settling, because the laws of the very small do not permit a clean zero. Under normal conditions, these flickers are far too small to matter, vanishing as fast as they appear. But this was not normal conditions. The expansion seized those microscopic flickers and stretched them, the same way it stretched everything, blowing a quantum tremor smaller than an atom up to the size of a galaxy and beyond, freezing it into the fabric of space before it could fade. So the expansion did something no smooth process should be able to do. It took the random jitter of the quantum world and printed it across the sky at enormous scale, converting the smallest imaginable fluctuations into a faint pattern of places where space held a little more energy and places where it held a little less. Those patches of slightly more and slightly less are not a footnote. They are the seeds of everything. Every galaxy, every cluster, the entire web of structure strung across the cosmos, all of it grew from those stretched quantum tremors, because a region with a hair more energy pulls a little harder, gathers a little more, and over billions of years that head start becomes a galaxy, while its emptier neighbor becomes a void. The largest structures in existence are quantum flickers, caught mid-flicker and frozen at cosmic size. This expansion was a cold event. The universe during it was nearly empty of ordinary matter and light, its energy still locked in that stuck symmetric state, still unreleased, still latent. A whole cosmos, ballooning by 26 zeros and running cold the entire time, its true energy held back like a held breath. Which leaves the obvious loose thread, that trapped energy, the latent heat of a transition that never finished, was still in there, enormous and waiting, and a system marooned above its true low-energy state cannot stay marooned forever. When that stuck state finally lets go and falls, where does all of that pent-up energy go? Picture the ball that had been marooned high on the hill, refusing to roll, holding all that latent energy locked in place while space ballooned cold around it. At last it lets go. It rolls down toward the bottom, toward the true low-energy state it should have reached long before, and the enormous energy difference between where it was and where it lands has to go somewhere. It does not vanish. Energy never vanishes. It converts. And what it converts into is everything. The falling did not happen cleanly, and the mess is the whole point. A ball rolling into a valley does not stop dead at the bottom. It overshoots, climbs the far side, falls back, rocks back and forth across the low point, sloshing again and again before it finally settles. The energy field that had been trapped did exactly this, plunging past its low point and oscillating around it, swinging back and forth across the bottom of that valley at a staggering rate. And every one of those swings shed energy, because a field sloshing like that cannot hold the energy in. It pours it out. It pours it out of particles. Energy becoming matter, the same trade that made pairs of particles in the fireball, except here, the source is not photons colliding, but a giant field unloading its stored energy as it rocks toward stillness. Each oscillation of that field dumped energy into the creation of particles, filling a universe that a moment earlier had been nearly empty and cold, filling it with a dense, seething crowd of matter and radiation. The hot, dense, particle-filled fireball, the thing the words Big Bang actually conjure, did not begin at the wall. It began here, when the trapped energy fell and reheated an empty, cold universe into a furnace. The universe had gone cold during the expansion, its real energy locked away out of reach, so that ballooning cosmos was frigid and nearly empty. Reheating is the instant that reverses. The locked energy releases, converts into a swarm of particles, and the temperature of everything rockets back up from near nothing to a heat beyond the core of any star. The furnace was not lit at the beginning of the expansion. It was lit at the end of it, by the very energy that had driven the expansion in the first place. The thing that made space balloon is the same thing that then filled it with fire. At the heat reheating produced, collisions between particles carried enough energy to do what we described at the very start, to turn light into matter and matter back into light, freely, in both directions. The universe was hot enough to manufacture particles out of pure energy again, hot enough that the two-way traffic of creation and annihilation ran at full speed. So reheating did not just fill space with particles once. It set the temperature high enough that particles and radiation kept trading places, a churning equilibrium of everything turning into everything, all governed by that same relationship between how hot it is and how much energy each collision can spend. That the expansion happened, and that the universe emerged from it hot and full of particles, the evidence supports strongly because the seeds of structure we can actually measure match what a stretched and reheated universe predicts. But the exact identity of the field that got trapped and then fell, its precise properties, the fine details of how it sloshed and what it made as it settled, those remain open. There are many candidate versions, and we cannot yet point to one and say this was the field. The shape of the story is firm. The face of the field that drove it is still in shadow. When you make particles out of pure energy, you cannot make them one at a time, cannot conjure a lone particle of matter from a burst of energy. The books have to balance. Every particle of matter comes into being paired with a particle of antimatter, its exact opposite, born together so that what went in as neutral energy comes out as a matched, canceling pair. This is not a quirk of reheating. It is a deep rule about how energy turns into matter anywhere, the same rule that governed the fireball, the same one we watch enforced in accelerators today. Energy in, balanced pairs out. Always. So reheating handed the young universe a perfectly balanced ledger, and that is precisely the trouble. A furnace full of particles, yes, dense and blazing and alive with matter, but every particle of matter shadowed by its antimatter twin, and we already followed where that leads. A perfectly balanced universe annihilates itself back to light and leaves nothing behind. The reheated cosmos, for all its fire, was still sitting on that knife's edge, still fated for emptiness, unless something, somewhere in the rules, quietly favored matter over its opposite by the faintest possible margin. These particles had mass, some of them heavy, some light, some with no mass at all. We have been saying the word mass all night, as though it were obvious what mass is, as though of course a particle weighs what it weighs. But nothing we have said explains where mass comes from, why one particle is heavy and another weighs nothing and moves forever at the speed of light. The furnace was full of particles with mass. What in the universe had just decided how much each one would weigh? Mass is not a thing a particle has. It is a thing that happens to a particle. We carry the opposite intuition without ever examining it. The sense that weight is built into an object the way color seems built into a painted wall, a fixed property it simply owns. But at the level of the particles the furnace made, mass is not owned at all. It is granted, from outside, by something the particle is moving through. Strip that something away and the heaviest particle in your body would weigh exactly nothing and fly off at the speed of light, unable to slow down, unable to stop, unable to be part of anything that holds still long enough to be called matter. To see why, start with what mass actually does. Mass is resistance to being pushed. A heavy thing is hard to get moving and hard to stop once it moves, and a light thing yields to the faintest shove. That resistance is the whole of what mass is, physically. Not bulk, not size, but reluctance to change how you are moving. A particle with no mass has no such reluctance at all, and a particle with no reluctance cannot do anything but move at the one speed the universe allows for things that cannot slow down, the speed of light, forever, never resting. So the question of where mass comes from is really the question of where that reluctance comes from. What makes a particle hard to push? The answer is that space is not empty, even where it looks emptiest. Filling all of it, every cubic inch of the room around you and the space between the stars alike is a field, switched on everywhere, quietly present in what we call the vacuum. Some particles interact with this field strongly, some weakly, some not at all. And how strongly a particle interacts with it is exactly what determines the particle's mass. Interact strongly, and the field drags on you, resists your acceleration, makes you hard to push. That resistance is what we weigh and call mass. Interact not at all, and the field ignores you completely, and you sail through at light speed with no mass whatsoever, which is precisely what light itself does. The mechanism, stripped down, is a resistance that depends on how much you engage with what fills the room. Move through a crowd where nobody knows you, and you cross easily, no one slowing your step. Move through the same crowd as someone everyone stops to greet, and you are constantly delayed, your progress dragged down, effectively made heavier by all the attention. The crowd has not added bulk to you. It has added resistance, and resistance is what mass is. The particles we call heavy are the ones this field crowds around and clings to. The particles we call light barely draw its notice, and light itself moves through untouched, greeted by no one, and so stays massless and unstoppable. That is the whole idea, and the strength of each particle's engagement with the field, written as a single number for each kind of particle, sets how much it weighs. This field was not always switched on. In the blazing heat, just after reheating, the field that grants mass was in its symmetric state, its value sitting at zero everywhere, engaging with nothing. And in that era, every particle was massless, all of them racing at light speed, none able to slow or settle. Then the universe cooled through another of its thresholds, and the field did what the freezing water did. It broke its symmetry and settled into a new value, no longer zero, switching on across all of space at once. This is the same phase transition idea again. Another symmetry breaking at another temperature. And the moment it happened, particles that had been massless suddenly felt the field's drag and gained the mass they carry now. For the first fraction of a second, nothing weighed anything. Mass switched on only when the universe had cooled enough for that particular field to freeze into its active state, a definite moment tied to a definite temperature, just as every splitting of forces was. Before that threshold, a universe of massless particles all moving at one speed. After it, a universe where particles have weight spread across an enormous range, some nearly nothing, some thousands of times heavier than others, each weight set by how tightly this one field decided to hold it. The variety of masses in your body traces back to a single field's differing grip on different particles, frozen in at one instant of cooling. Feel the weight of your own body against whatever is beneath you right now, and let that sensation mean what it actually means. That pressure, the sense of being held down, of having heft, is your particles being reluctant to move, and that reluctance is them engaging with a field switched on everywhere in this room, the same field that switched on across the whole universe when it cooled past that threshold. Your weight is not a private fact about you. It is a reading of how strongly the particles you are made of are gripped by something filling the space you lie in. The heaviness pinning you to the bed is the vacuum itself, holding on to you. But notice what mass does and does not explain. Mass tells each particle how hard it is to push. It says nothing about whether the particle should exist at all. The furnace made matter and antimatter in balanced pairs, and switching on their mass changed how heavy each was, not how many there were. Every particle of matter still had its antimatter twin, now both endowed with mass, still fated to find each other and annihilate back into light, still leaving a universe of radiation and nothing else. Mass gave the actors their weight. It did not decide which actors would survive the night. So the deepest imbalance of all is still waiting, unexplained. Out of perfectly matched matter and antimatter, how did matter come out even one part ahead? Start with the number itself. For every billion particles of antimatter the young universe made, it made 1,000,001 particles of matter. One extra out of 1,000,000,000. That is the entire margin by which anything exists. When the universe cooled below the temperature that kept manufacturing pairs, the great annihilation began. Every particle finding its antiparticle and vanishing into light, 1,000,000,000 pairs erasing themselves for each lone survivor left standing. And those survivors, that thin residue of 1 in 1,000,000,000, are the whole material world. Fill a stadium with 200,000 people, then imagine matter and antimatter pairing off and walking out together, canceling each other one couple at a time until the seats empty. On that scale, 1,000,000,000 to 1 means you would need 5,000 stadiums, 1,000,000 people each, and after every possible pair had left, you would find one single person remaining across all of them, alone in an ocean of empty seats. Everything you have ever touched is built from survivors that rare. The rest of the crowd did not go anywhere. It turned to light, and that light is still here, which is a thread we will pick up before this is over. So the question sharpens. Not why is there matter, but why is there that faint excess of matter, when everything about how energy makes particles insists on perfect balance? Every time we watch energy turn into matter, in the fireball, in reheating, in accelerators today, it comes out in matched pairs, one particle and one antiparticle, the ledger balanced to 0. A universe that only knows how to make balanced pairs should contain exactly as much antimatter as matter, and should therefore annihilate itself to nothing. For 1,000,001 to come from 1,000,000,000, some process in the early universe had to break that balance, had to make matter just slightly more readily than it made antimatter. In the 1960s, the Soviet physicist Andrei Sakharov worked out what any such process would require, and reduced the whole problem to 3 conditions that must all hold at once. They are strict, and each one rules out an easy version of the answer. The first is that there must exist some process capable of producing an imbalance at all, some interaction that can leave behind more matter than antimatter, rather than always creating and destroying them in lockstep. If the universe can serve the balance perfectly under every possible interaction, No excess could ever appear, no matter how the dice fell. There has to be a door through which an imbalance can even walk. The second condition is the subtle one, and it is where the real difficulty lives. It is not enough that a process can make an excess. That process must also treat matter and antimatter differently, must favor one over the other, even slightly. Because if the laws of physics were perfectly even-handed between matter and antimatter, then any process that produced a little extra matter in one place would be exactly mirrored by a process producing a little extra antimatter somewhere else, and the two would cancel, leaving the same balanced nothing. For matter specifically to win, the rules themselves have to be faintly lopsided, have to contain a built-in preference, a slight tilt toward matter woven into the interactions. The universe cannot be neutral. It has to take a side. The third condition is that all of this had to happen while the universe was out of balance in a different sense, thrown out of its smooth thermal equilibrium. A universe sitting in perfect thermal balance runs every reaction as often backward as forward, and a preference expressed in the forward direction gets quietly undone in reverse. Only when the universe is changing fast, cooling and expanding too quickly for reactions to keep pace, can an imbalance made in one instant survive instead of being erased the next. The rapid cooling we have followed all night is not a side detail here. It is the third ingredient, the thing that let a momentary preference freeze into a permanent excess before it could reverse. Here is where the honesty has to come in, because the three conditions are the settled part, and what fills them is not. We have actually found the second ingredient in the laboratory, the faint lopsidedness between matter and antimatter. Watching certain rare particles decay, physicists saw matter and antimatter versions decay at slightly different rates. The rules caught in the act of not being perfectly even-handed. That tilt is real, measured, confirmed more than once. But when you tally how much lopsidedness those measured effects provide, it falls short of what is needed, and not by a little. The known preference is far too small to account for 1,000,000,001 from 1,000,000,000. The tilt exists. It is nowhere near steep enough. We know the three conditions that any answer must satisfy. We have confirmed that the hardest of them, the built-in preference for matter, is not zero. And we still cannot fully explain how the excess got as large as it did, because the preference we can measure is too faint by many orders of magnitude to do the job. Something else is contributing. Some process or some particle we have not yet pinned down, tilting the early universe toward matter far more strongly than anything we have caught in an accelerator. The survivors in your hand are proof the tilt was steep enough. We just cannot yet say what made it so. 1,000,000,000 pairs annihilated for every survivor, and each annihilation poured its matter back into light. That light did not leave. It cooled and stretched with the expanding universe, and it is still arriving. The same faint bath soaking every direction of the sky. Hundreds of millions of those photons crossing your body every second. For each particle of matter in existence, there are roughly 1,000,000,000 of those photons, and that ratio is not a coincidence. It is a head count of the annihilation. Every photon in that ancient glow is the ash of a matter particle that met its antimatter twin and lost. The faint warmth of the early universe, still washing through this room, is the light of almost everything that used to exist. But the survivors that remained were not yet the particles we would recognize. The matter that won was still too hot to assemble itself into anything stable, its most basic pieces still unbound, still dissolved in a state so extreme that the protons and neutrons at the core of every atom did not yet exist. Those winners were quarks, loose and free in a searing plasma, and they could not simply be counted and set aside as protons. Something still had to gather them, to lock them into the heavy particles that would anchor all matter. What was that plasma? And what forced it to finally freeze into the protons and neutrons we are built from? The winners of that great annihilation could not yet be called protons, because protons did not exist. What survived was more basic, a kind of matter that no longer appears anywhere in the universe today, except when we force it into being for a fraction of a second in a machine. The heat was still so extreme that the building blocks of matter could not hold together into anything larger. They stayed loose, unbound, dissolved in a plasma of pure ingredients. Those ingredients were quarks, the pieces that make up protons and neutrons, and alongside them the particles that carry the strong force. And in that furnace they all moved freely, none of them locked into the tidy triplets we find at the heart of matter now. To understand why they could roam free then and never can now, you have to meet the strangest behavior of any force in nature. The strong force, the one that binds quarks, does something no other force does. It gets stronger as quarks move apart. Every force you have any intuition for weakens with distance. Step away from a magnet and its pull fades. Drift from a planet and its gravity loosens. The strong force runs backward. Up close, when quarks are jammed together, the force between them is oddly gentle, and they slip around almost as if they were free. Pull them apart, and the force grows, hauling harder the farther they get, like a spring that stiffens the more you stretch it. You can never pull a single quark out on its own. Try to, and as you drag a quark away from its partners, the strong force between them stores more and more energy, exactly the way stretching a spring stores energy in the pull. And this is where the equation from the start of the night walks back on stage, because stored energy is not weightless. Energy is mass. Pour enough energy into that stretching bond, and at some point there is enough of it to become matter. And the bond does precisely that. It snaps, and the energy you poured in by pulling converts into a fresh pair of quarks, one capping each broken end. You reached in to isolate one quark and came away with two pairs. You can never hold just one. The pulling itself manufactures new partners out of the energy of the pull. Picture stretching a rubber band, expecting that if you stretch it far enough, it must eventually snap into two loose ends. Instead, the instant it breaks, each end seals itself into a brand new, complete rubber band, and you are left holding two whole bands where you tried to make loose ends. Break those, and you get four, each one whole, never an unattached end anywhere. That is what confinement means. Isolated quarks are not just hard to find. The very act of trying to separate them spends energy that becomes new quarks, so a lone quark is something the strong force will not permit to exist. Every quark spends its life bound to others, always. So in the young furnace, why were quarks free? Because at that ferocious temperature they were packed so densely and moving so violently that they were always close to one another, and up close the strong force is gentle. There was no pulling apart, no room to stretch a bond and pay the price, because every quark was already jammed against countless neighbors. The plasma was a sea of quarks so tightly crowded that none of them could be meaningfully said to belong to any one partner. This is the quark-gluon plasma, and it is the actual state the surviving matter was in. Not protons yet, a seething, bound to no one soup of the pieces protons are made from. Then the universe crossed another threshold, and this one built the heavy particles at the core of everything you are. At around 1/10,000th of a second after the beginning, the plasma cooled and thinned enough that quarks were no longer jammed shoulder to shoulder. Gaps opened. Quarks found themselves with room to move apart, and the moment they did, the strong force could finally do its stiffening work. It hauled them together in threes and locked them there, and those triplets are protons and neutrons. 3 quarks bound so tightly that nothing since has ever pried one loose. The confinement that rules matter today switched on here, at this cooling, freezing the free quarks into the bound triplets that would anchor every atom. And now the fact that reorders how you think about your own body. Add up the mass of the 3 quarks inside a proton, the actual weight of the pieces themselves, and it comes to a tiny fraction of the proton's mass, around 1%. The other 99% is not made of stuff at all. It is the energy of the strong force binding those quarks together, the roiling energy of the bond itself, converted into mass by the same equation that has run through everything tonight. The quarks got their small masses from the field we met before, the one that switched on and dragged on them, but that accounts for almost nothing of what a proton weighs. Nearly all of a proton's mass is bound energy wearing the disguise of matter. This is the one that stops me cold every time I come back to it. Nearly all of your weight, the heft you feel pressing into the bed, is not substance, it is energy. The ceaseless straining of the strong force inside every proton and neutron in every atom of you, frozen into mass. The small part that traces to the mass-giving field, the weight the quarks and electrons actually carry as particles, is almost a rounding error. When you feel how solid your own hand is, you are feeling something that is barely there as matter and almost entirely there as bound energy, energy locked into place at that 1/10,000th of a second when the quarks stopped being free. You are far more energy than thing. But the protons and neutrons that just froze into being were not equal, and the difference between them started a clock. A neutron is a touch heavier than a proton, and in physics, heavier means less stable, more inclined to fall apart into lighter things. The instant-free neutrons existed. They were already living on borrowed time, each one liable to decay into a proton, and the universe now had only a narrow window to do something with its neutrons before they slipped away. Everything heavier than the simplest hydrogen would depend on catching them in time. What was the universe racing against? And why did so much hang on a difference in weight so slight it barely registers? The universe was racing against its own neutrons, and the finish line was a temperature. A free neutron, one not locked inside a nucleus, does not last. Left alone, it falls apart, turning into a proton and shedding the extra bit of mass that made it heavier, with an average lifetime of about 15 minutes. 15 minutes sounds generous until you remember the pace of everything else here, where the important thresholds arrive in seconds and fractions of seconds. Every neutron that decayed was a neutron lost to the making of anything heavier than plain hydrogen, and the universe needed those neutrons. So the clock that started when protons and neutrons froze into being was, from the first instant, a countdown. But before the countdown could matter, something had to set how many neutrons there were to begin with, and that number was decided by a balance that held only while the universe stayed hot. In the heat, just after the quarks locked into protons and neutrons, the two kinds could still turn into one another freely. A proton could absorb a passing particle and become a neutron. A neutron could shed one and become a proton, and these conversions ran constantly in both directions, keeping the two populations in a shifting balance. If the two had been equal in mass, that balance would have sat at 50-50, but the neutron is slightly heavier, and making a heavier particle costs a little more energy, so at any given temperature the universe found it slightly easier to make protons than neutrons. The balance tilted toward protons, and how far it tilted depended entirely on the heat. 小于二井号大于. How much harder it is to make the heavier neutron depends on the ratio between the neutron's mass penalty and the energy available at that temperature. While the universe was blazing hot, that mass penalty was trivial next to the energy in every collision. So neutrons and protons were made almost equally, close to 50-50. As the universe cooled, the energy in each collision dropped. The neutron's extra mass loomed larger as a fraction of what was available, and neutrons grew steadily harder to make. The tilt toward protons deepened with every degree of cooling. The proportion of neutrons was sliding downward, tracked precisely by the falling temperature. This sliding balance would have kept going, neutrons dwindling toward almost none, except that the conversions themselves depended on a force that was about to bow out. The reactions turning protons into neutrons and back are governed by the weak force, the short-ranged one behind radioactive decay, and the weak force is feeble and lazy. It only acts when particles are crowded densely enough to interact often. As the universe expanded and thinned, the particles that drove those conversions grew too sparse to keep finding each other, and the conversions slowed and then effectively stopped. At about 1 second after the beginning, the balance simply froze. Whatever ratio of neutrons to protons happened to exist at that instant was locked in, because the reactions that could have changed it had shut down. The universe stopped adjusting the number. Roughly 1 neutron for every 6 protons, frozen in place. And it happened because of the particles that carried those weak interactions, particles we have not yet named, neutrinos. Neutrinos are the ghostliest things in physics, almost massless, interacting so weakly that they pass through matter as if it were not there. Right now, trillions of neutrinos from the sun are streaming through your body every second, and essentially none of them touch a single atom of you. They cross the whole Earth as easily as light crosses glass. While the early universe was dense enough, even these barely interacting particles were forced to interact, packed so tightly they could not avoid one another. They were what kept the proton-neutron conversions running. When the universe thinned past a certain point, the neutrinos stopped interacting too, and they did something the rest of matter would not do for hundreds of thousands of years yet. They went free. At around that same 1 second mark, neutrinos decoupled from everything else, ceasing to collide, simply streaming outward through the expanding universe without touching anything ever again. They have been streaming ever since. That release created a background of neutrinos filling all of space, a flood of them left over from the universe's first, second, and by the same logic that stretched and cooled the light of the fireball, this neutrino background has cooled too, chilled by all the expansion since to just under 2 degrees above absolute zero. It is still here, everywhere, right now. A sea of particles set loose when the universe was 1 second old, passing through this room and through you as you lie here. That neutrino background is a direct message from the universe at 1 second of age, older than the oldest light we can see by hundreds of thousands of years. It would be the earliest relic we could ever hope to hold. And we almost certainly never will. The very ghostliness that let neutrinos go free so early, their refusal to interact, is exactly what makes this ancient background nearly impossible to detect. These relic neutrinos are so low in energy now that they slip through every instrument we can imagine building, carrying their message from the first second and refusing to deliver it. We know the sea is there. The physics leaves no room for it to be absent. We simply cannot reach in and touch it. So, the departure of the neutrinos left the universe with its neutron count frozen, 1 for every 6 protons, and the countdown running hard. Those neutrons were decaying, 15 minutes of average life each, the supply bleeding away with every passing second. To save any of them, to build anything heavier than lone hydrogen, the universe had to lock them into nuclei before they decayed, and locking them in required fusion, and fusion required the temperature to fall into a narrow window. Too hot, and any nucleus that formed would be blasted apart instantly. The universe had to cool enough to let nuclei survive, but do it fast, before the neutrons were gone. A race between a falling temperature and a draining supply of the one ingredient that everything heavier depended on. The window opened about 3 minutes in. By then, a good fraction of the neutrons had already decayed. The 1 in 6 thinned further by the weight, and what remained had only a brief opening in which to be saved. For a few minutes, and only a few, the universe would run as a fusion furnace, building the first nuclei out of the neutrons that had survived the countdown. What it built in those minutes fixed the raw composition of all ordinary matter, everything the stars would later have to work with. What determined which nuclei formed in that narrow window, and why did the building stop almost as soon as it began? The building of the first nuclei should have started long before 3 minutes, and the reason it could not is a debt left over from the annihilation. The simplest step toward anything heavier than hydrogen is to bind one proton to one neutron. That pair is the first rung, the doorway every heavier nucleus has to pass through. And that first pair is fragile. The bond holding a proton to a neutron is weak, easily shattered, and in the young universe there was something everywhere that shattered it. Light. The same enormous flood of photons left over from the annihilation, 1 billion of them for every particle of matter, and at these temperatures each one still carried enough energy to blow that delicate first pair apart the instant it formed. Remember that for every surviving particle of matter, the annihilation left about 1 billion photons. That 1,000,000,000 flood was the price of our existence, the reason there was any matter left over. But that same flood now stood in the way. With 1 billion photons hounding every proton and neutron, the moment a proton and neutron managed to bind, one of those countless photons would slam into the new pair and break it apart again, faster than the next pair could form. The very abundance of light that proved matter had won was now preventing that matter from assembling into anything. The excess we are made of, and the delay in making us trace to the same 1,000,000,000 to 1. So the universe had to wait, not for more neutrons, but for the light to weaken. Binding could not begin in earnest until the universe cooled far enough that most photons no longer carried the energy to break that first fragile pair. That is what 3 minutes bought. Not the moment fusion became possible in principle, but the moment the light finally dimmed enough that a proton-neutron pair could survive long. The delay was never about the ingredients. It was about clearing the destroyers out of the way, and the destroyers were the leftover glow of everything that had annihilated. The instant that pair could hold, everything happened at once. With the first rung stable, the reactions raced up the ladder almost explosively. A proton and neutron bound together, then caught another proton, then another neutron, assembling in a rapid chain into the next stable nucleus and the next. The chain ran hard toward one particular destination, a nucleus of 2 protons and 2 neutrons, an exceptionally tight and stable package. That is the nucleus of helium, and it is a deep well that the reactions poured into readily. Almost every neutron that had survived the countdown ended up locked inside one of these helium nuclei, sheltered there, safe at last from decay. Bound into a nucleus, a neutron no longer falls apart. The countdown ended for every neutron that made it inside. Now the proportion falls out with a simple logic, and it is one of the quiet triumphs of the whole theory. By the time building began, the frozen 1 in 6 ratio had thinned further through decay, leaving roughly 1 neutron for every 7 protons. Each helium nucleus swallows 2 neutrons and 2 protons. So take those neutrons, pair each with a proton, and lock them into helium 2 at a time, and nearly all the neutrons vanish into helium while most of the protons are left over with no neutron to pair with. those leftover lone protons are hydrogen. Count it up and it lands, with no room to wiggle, at close to 3/4 of the mass as leftover hydrogen and 1/4 as helium. That ratio was written the moment the neutron count froze, and it is exactly the ratio we measure in the oldest gas in the universe today. The prediction and the observation meet on the same number. The universe made hydrogen and helium and then, essentially, quit. A trace of the next element up, lithium, and almost nothing beyond. Not because the fuel ran out, though it was thinning. The deeper reason is a gap in the ladder itself. To build heavier elements, the reactions would have needed to pass through nuclei of 5 particles and of 8 on the way up, and nature provides no stable nucleus with exactly 5 particles, and none with exactly 8. Those rungs are missing. A nucleus that size falls apart almost the instant it forms, before it can catch the next piece. The ladder to heavier elements has 2 broken rungs right at the bottom, and the racing chain of reactions hit them and could climb no further. The early universe, for all its heat and fury, could only make the 2 lightest elements in any quantity, hydrogen and helium, and then a wall. Every heavier thing, every atom past helium, could not be built in those 3 minutes. Not the carbon in your cells, not the oxygen you are breathing right now, not the calcium in your bones or the iron in your blood. None of it was made in the beginning. The universe handed itself only the 2 simplest ingredients and then hit a barrier it could not cross. And it would take hundreds of millions of years and the fusion cores of entire stars and their violent deaths to bridge those broken rungs and forge everything heavier. The beginning made almost nothing you are made of. It made the raw hydrogen and stopped. We tend to imagine the birth of the universe as the origin of everything, the moment all the material of existence came into being. It was not. The first few minutes made only the lightest scraps, 2 elements and a whisper of a third, and then reached a limit it could not pass. The universe that emerged from its fiery beginning was almost entirely the simplest possible matter, a vast thin fog of hydrogen with a 1/4 measure of helium mixed through it, and nothing else of any consequence. Everything intricate, everything that could ever become a planet or a cell or a person, had to wait for stars that did not yet exist. The beginning was not a moment of endless creation. It was a moment that made the plainest thing it could and then stalled. And having made that thin hydrogen fog, the universe went quiet in a way it had not been before. The frantic era of thresholds and freezings was ending. The nuclei were set, the composition fixed, and now the cosmos entered a long stretch where, at first glance, almost nothing seemed to happen at all. But that quiet was not empty. Beneath the stillness, the fog of matter and the ocean of light left over from the annihilation were locked together, pressing on each other, and the whole vast mixture was doing something no one would guess from the outside. It was ringing, like a struck bell, for hundreds of thousands of years. What was pressing on what to make a whole universe ring? For hundreds of thousands of years, the universe was a fluid, and that word is meant almost literally. The matter, still bare nuclei and loose electrons too hot to join, was bound tightly to the ocean of light left over from the annihilation, so tightly that the 2 behaved as a single substance. Light and matter, locked together, moving as one. The photons could not travel freely because they were forever colliding with the loose electrons. And the matter could not move without dragging the light along, and the light could not press without shoving the matter. They were welded into one fluid, and like any fluid, it could carry a wave. To see the wave, follow what happens to a single dense spot. The universe was not perfectly smooth. It carried those faint patches of slightly more and slightly less that had been stretched to cosmic size during the early expansion, the seeds we followed before. Take one of the denser patches. Gravity pulls matter inward toward it, trying to make it denser still, exactly the runaway gathering that builds structure. But this matter was welded to light, and light does not allow itself to be crushed quietly. As gravity squeezed the matter inward, the trapped photons pushed back, their pressure resisting the compression, until the outward shove of the light overwhelmed the inward pull of gravity and blew the whole region back outward. Then, expanded and thinned, gravity took over again and pulled it back in and out, compression and rebound. That is an oscillation, and an oscillation in a fluid is a sound wave. This was not sound as a metaphor. A sound wave is precisely this, a pattern of compression and thinning traveling through a medium, air pressing and easing against your eardrum. The early universe was doing the same thing on an enormous scale, regions compressing and rebounding, pressure waves rolling outward through the welded fluid of light and matter. The whole cosmos was filled with these waves, a vast overlapping chord of them rolling out from every dense patch at once. If you could have stood inside it with ears that worked in that medium, the universe would have been ringing, an immense and tuneless sound filling all of space. And these waves moved with astonishing speed because of what the fluid was made of. The speed of a sound wave depends on what it travels through. Through air it crawls, a few hundred meters a second, because air is loose and slow to spring back. This fluid was almost entirely light, and light springs back with the fiercest pressure there is. A wave rolling through a medium made mostly of photons travels at close to 60% of the speed of light itself. These were sound waves moving at a fair fraction of the ultimate speed limit, racing outward from every dense seed. In the time the universe stayed a welded fluid, a single one of these waves could travel an enormous distance, a wave front expanding for hundreds of thousands of years at nearly the speed of light. Each dense seed sent a spherical sound wave rolling outward through the fluid, a shell of compressed matter and light expanding away from the original spot. That shell kept expanding for as long as the light and matter stayed welded together, and then, at a certain moment we are about to reach, the welding broke. The light went free, and without the light to carry it, the sound wave stopped. Every expanding shell froze exactly where it was at that instant, leaving a ring of slightly denser matter at a fixed distance from each original seed, a distance set by how far a sound wave could travel in the time before the light escaped. That frozen distance is a real length, and it is still stamped across the sky. The rings never went away. At the center of each, and in the ring around it, matter was slightly denser, and denser matter is where galaxies preferentially form. So galaxies today are subtly more likely to sit at that special separation from one another, the frozen radius of those ancient sound shells, a preferred distance woven into the arrangement of galaxies across the whole universe. When astronomers survey millions of galaxies and measure how they cluster, that preferred separation shows up in the data, a faint but unmistakable excess at one particular distance. A sound wave that rolled through the first few 100,000 years left a ruler behind, and we can read the ruler by mapping where galaxies sit. The pattern of galaxies across billions of light years is not random, and it is not only the work of gravity gathering matter. It carries, printed into it, the frozen echo of sound waves from when the universe was an infant. The clustering of galaxies is sheet music from the first 300,000 years, a chord struck in a fluid of light and matter and then frozen the moment the light broke free, still legible in the sky tonight. We are not looking at silence when we map the galaxies. We are looking at a sound held still for 13 billion years. And this frozen ruler does more than astonish. It works for us as a tool. Because we can calculate exactly how far those sound waves should have traveled, we know the true size of that ruler. And by comparing its true size to how large it appears in the sky at different distances, we can measure the shape and expansion of the universe with a precision almost nothing else provides. The sound of the early universe became one of our most reliable instruments for weighing the cosmos. A standard length laid down by physics we understand, waiting in the galaxy maps for us to use it. The ringing did not just leave a record, it left a measuring stick. Everything in this ringing fluid was smooth, or nearly so, the densest patches only a hair denser than their surroundings. But nearly is not the same as perfectly, and in a few rare places the physics allowed something far more extreme than a sound wave. If a region were dense enough, not a hair above its surroundings but wildly, violently above them, gravity there would not simply gather matter into a ring. It would win outright, crushing the region into itself before any pressure could push back. That collapse would make an object no star was needed to build, an object that could exist before the first star ever formed, in the middle of a universe still too young to have made one. What kind of thing can gravity build out of nothing but the early universe itself, with no star required at all? Gravity can build a black hole with no star at all, and the early universe was the one place in all of history where it could do this easily. We are used to black holes as the corpses of massive stars, formed when a giant runs out of fuel and its core collapses under its own weight. That path needs a star, and stars did not yet exist. But a star is only one way to pile enough matter into a small enough space. The early universe offered another, because for a brief window it was denser everywhere than the core of any star that would ever live. In a cosmos that crowded, you do not need a star to gather the matter. The matter is already gathered. You only need one region to be crowded a little more than the rest. To see why that is enough, think about what makes a black hole in the first place. A black hole forms when matter is packed so tightly that the pull of its own gravity becomes impossible to escape, when the speed you would need to fly away from it exceeds the speed of light, and since nothing outruns light, nothing gets out at all. How much matter you need for this depends entirely on how tightly it is squeezed. Pack it loosely, and you need a mountain of it. Pack it fiercely enough, and a small amount will do. There is a precise line for any lump of matter, a size below which, if you compress it past that point, it can no longer hold itself open against its own gravity and collapses into a black hole. For the Earth, that line is about the size of a marble. Squeeze the whole planet smaller than a marble, and it would become a black hole. Nothing squeezes the Earth that hard, so it never will. But the infant universe squeezed everything that hard and harder, everywhere, all at once. In the first fraction of a second, the density of the whole cosmos was beyond anything a star ever reaches, and here is the opening. That density was not perfectly even. It carried the same faint ripples we have followed since they were stretched out of quantum flickers, regions a little denser and a little thinner threaded through everything. In most places the excess was tiny, a hair above average, far too gentle to collapse. But the ripples were random, and in a random field, most variations are small, while a rare few are enormous. Somewhere, in the rarest places, a region might have been not a hair denser, but overwhelmingly denser, dense enough to cross that line. Where that happened, the region did not wait for anything. It collapsed on itself immediately, right there in the opening moments, folding into a black hole while the universe was still too young to have made a single star. These are what we call primordial black holes born straight from the unevenness of the early universe, needing no star, no fuel, no death, only a patch of the infant cosmos that happened to be crowded past the breaking point. And because the density of the universe was changing so fast in those first instants, the size of these black holes would depend on exactly when they formed. Form in the very first slice of a second, and you get something tiny. Form a little later, when the region enclosed more, and you get something far heavier. This possibility has been known for decades, and for most of that time it stayed a possibility, neither confirmed nor ruled out. The appeal is that primordial black holes could quietly solve more than one mystery at once, and the deepest of these is the question of what most of the universe is made of. Most of the matter in the cosmos is invisible, giving off no light, revealing itself only by its gravity, and we do not know what it is. Primordial black holes are dark, give off no light, and pull with gravity. So the tempting idea is that the dark matter holding galaxies together might be nothing exotic at all, just an enormous population of black holes forged in the first second, hiding in plain sight ever since. The honest state of that idea is that most of it has been closed off, but not all. If black holes of a given size were common enough to be the dark matter, they would leave marks we could check for. A black hole passing in front of a distant star briefly bends and brightens its light in a way we know how to look for, and surveys watching millions of stars have not seen nearly enough of these brief brightenings to account for the dark matter with black holes of most sizes. Those searches have ruled out one mass range after another, yet a few narrow windows remain, particular sizes where primordial black holes could still, in principle, make up a large share of the dark matter without having been caught yet. The idea is wounded, not dead. It survives in the gaps our searches cannot yet reach. There is a second reason these objects draw so much attention now, and it reaches into what our newest telescopes are seeing. When we look at the very early universe, we find something that is hard to explain. Enormous black holes already grown to millions of times the mass of the Sun when the universe was only a few 100 million years old, far too soon for them to have grown that large by the slow feeding we understand. A black hole grows by swallowing matter, and there is a speed limit on how fast it can swallow, and that limit seems too slow to build a giant so early, unless the giant did not start from a stellar corpse at all. If some black holes began as heavy primordial seeds, born already massive in the first second, they would have had a head start of hundreds of millions of years, enough to reach monstrous size by the time we see them. The earliest giant black holes might be the grown children of the first second. The very distant, very bright objects our newest telescope is finding are being argued over right now, and the arguments are real and unsettled. Some of those bright points may be giant black holes feeding fiercely. Some may be dense knots of stars masquerading as something more exotic. Some may be a mix we do not yet understand. Whether any of them are grown primordial black holes is exactly the kind of question that gets answered slowly, by many measurements, not by one striking image. What is solid is only this: the early universe could make black holes with no star involved. The physics of it is sound, and whether it actually did, and in what numbers, is a live question our instruments are circling right now. So the infant cosmos may already have held these dark, collapsed objects, scattered rarely through a fog that was still, for the most part, doing something far gentler. Because even as a few extreme regions were folding into black holes, the rest of the universe, the ordinary fog of hydrogen and helium nuclei and loose electrons, was cooling toward a threshold of its own. Not a threshold of collapse, but of combination. For the first time, the pieces of matter were about to be able to join, nuclei and electrons drawing together into something neither had been before. Before the light could break free, before the first atoms could even form, the universe made something smaller and stranger. the very first time two atoms worth of matter ever bonded into a single molecule. What was the first molecule the universe ever made? And why was it built from the one element that almost refuses to bond with anything? The first molecule in the universe was built from helium, which is the strangest possible choice, because helium is the element that wants nothing to do with chemistry. Helium is the classic loner. It sits at the far end of the periodic table's first row as the original noble gas, the element famous for refusing to react, refusing to bond, refusing to join anything at all. A helium atom holds its two electrons in a closed, contented shell, perfectly balanced, with no hunger to share, or steal, or borrow. That completeness is exactly why it stays aloof. An atom bonds when it can lower its energy by pairing up, and helium is already at rock bottom, already satisfied, with nothing to gain. So the element least willing to bond is a bizarre thing to find at the very start of all chemistry. To understand how it happened, you have to know which atoms formed first, and the order is not the one you would guess. We tend to assume hydrogen came first, since it is the simplest and most abundant. But forming a complete atom means a nucleus capturing and holding on to electrons, and holding on is easier for some nuclei than others. Helium's nucleus carries twice the positive charge of hydrogen's, and that stronger charge grips electrons more tightly. So, as the universe cooled, helium was able to hold on to its electrons and become a complete neutral atom, while hydrogen still could not. Its nuclei still sat bare, unable to keep an electron against the surrounding heat. For a stretch of time, then, the universe contained neutral helium atoms drifting among still naked hydrogen nuclei, which are simply lone protons. A neutral helium atom, complete and aloof, found itself surrounded by bare protons, and a bare proton is not a satisfied atom at all. It is a naked positive charge, and a naked charge is desperate to grab whatever it can. So even helium, the atom that bonds with nothing, had something it could not fully resist. Its two electrons, though held tightly, still made a faint cloud of negative charge around it, and a passing proton, hungry and exposed, could be drawn to that cloud and cling to the edge of it. The proton latched onto the helium, and the two shared, lopsidedly, in a bond that helium would never have formed with a calmer partner. The result was helium and a proton joined. That joined object has a name, and it was the first molecule the universe ever made. Helium bound to a single proton, a helium atom with a hydrogen nucleus stuck to it, sharing electrons in the first true chemical bond in the history of everything. This happened remarkably early, within the first 100,000 years or so, before the universe had even finished making ordinary atoms, before the great release of the light. The first chemistry predates the first complete hydrogen atom. Chemistry, the joining of atoms into molecules, began not as a late flourishing once the universe had settled, but in the thick of the cooling fog, with the least sociable element in existence forced into a bond by a crowd of desperate protons. For a long time, this first molecule lived only in theory, and confirming it took nearly half a century. The reasoning that it must have formed was worked out in the 1970s, sound and compelling, but a prediction on paper is not the same as finding the thing itself, and this molecule is rare and hard to catch, long gone from a universe that has moved on to richer chemistry. It was not until 2019 that it was finally detected in space, not in the early universe, which we cannot revisit, but in a dying star's glowing shell of gas, a place where the same harsh conditions let the molecule briefly form again. There, in the light from that shell, was the unmistakable signature of the first molecule, confirmed at last, roughly 50 years after it was predicted. The universe's opening act of chemistry, written down long before anyone had ever seen it, and then caught in the act in a distant cloud. The chemistry inside you, the carbon linking into long chains, the oxygen and nitrogen and everything your body runs on, is a chemistry of eager, sociable atoms that bond readily and build endlessly. The universe's very first bond was the opposite of that, a reluctant, one-sided grip between an atom that bonds with nothing and a proton so exposed it would cling to anything. The starting point of all molecular complexity was the least likely partnership imaginable. Everything rich and intricate that chemistry would eventually become, every molecule that would ever matter to life, traces back to a first step taken by the one element that refuses to take steps at all. And this reluctant first molecule was a signpost of something larger unfolding across the whole universe at once. Its very existence meant the cosmos had cooled enough for nuclei to start holding electrons, for neutral atoms to begin forming, for matter to start becoming the calm, bound stuff we know instead of a searing plasma of loose charges. Helium had gone neutral, the first molecule had formed, and hydrogen, the most abundant matter in the universe by far, was sitting right at the edge of its own transformation, its bare protons on the verge of finally capturing and keeping the electrons they had been unable to hold. When hydrogen at last crossed that line, everything would change, because hydrogen was the material the light itself had been colliding with all along. That was the pivot the whole visible universe had been waiting for. For hundreds of thousands of years, the light had been trapped, welded through matter, unable to travel, because it kept slamming into the loose electrons that filled all of space. Those free electrons were the barrier. And the moment the protons finally captured them, folding the last free electrons into neutral hydrogen atoms, the barrier would simply vanish. The thing the light kept colliding with would be gone. After all this time welded into a glowing fog, the light was about to be set free in a single sweeping instant. What happens to a universe the exact moment it stops being able to trap its own light? The light broke free the moment the last electron found a home, and the timing of that moment is the strangest part. The barrier trapping the light was the loose electrons, the free negative charges scattered through all of space, and every photon kept colliding with them, unable to travel more than a short hop before being knocked off course. Clear the electrons away, bind them into neutral atoms, and the collisions stop. The light sails free. So the release of the light was really the disappearance of the free electrons, the instant nearly every one of them was captured by a proton and folded into a neutral hydrogen atom. You would expect that to happen the moment the universe was cool enough for a proton and electron to stick, and it did not. It happened far later and far colder than it should have. An electron bound to a proton sits in a well, and it takes a certain amount of energy to knock it back out. Cool the universe below the point where the average particle carries that much energy, and you would think electrons could settle in and stay. By that simple reckoning, atoms should have formed while the universe was still quite hot, thousands of degrees hotter than when they actually did, but they did not form then. The universe cooled past that point and stayed a plasma, its electrons stubbornly free, for a long time after they had any business remaining loose. Something kept knocking them back out, long after the average particle had gone too cold to do it. That something was the same flood of light we have met at every turn, the billion photons for every particle of matter. Think about what that ratio means here. For every single electron trying to settle onto a proton, there were a billion photons streaming past. And even when the universe had cooled so far that the average photon was far too weak to break an atom apart, a billion is an enormous number, and within any huge crowd of photons, there is always a rare tail of unusually energetic ones. With a billion photons per electron, even that rare energetic tail was still a vast multitude, more than enough to find each newly formed atom and blast its electron back off before it could stay. The average had gone cold, but the flood was so deep that its hottest fringe alone was enough to keep the whole universe ionized. So the same 1,000,000,000 that runs through this entire story struck one more time. That ratio was the price of our existence, the reason any matter survived the annihilation. It was the reason the first nuclei could not form until 3 minutes had passed, the flood breaking every pair as fast as it appeared. And now it was the reason the first atoms could not form until the universe was far colder still, the same flood, its energetic fringe tearing electrons loose long after the cold should have let them rest. One number, set in the first fraction of a second, reached forward and delayed both the building of matter and the making of atoms, holding the universe open and glowing for hundreds of thousands of years past when it seemed ready to go dark and quiet. The universe had to cool to around 3,000 degrees, not the much higher temperature simple logic suggested, before even that energetic fringe of photons finally lacked the strength to keep breaking atoms apart. 3,000 degrees is still hot, about half the temperature of the surface of the sun, a heat that would vaporize any solid thing. And yet that is how cold the universe had to fall before its own light loosened its grip on its own matter. When it finally did, the change swept through everything with startling speed. Across the whole universe, in a relatively brief span, protons captured electrons, atoms formed nearly everywhere at once, and the free electrons that had blocked the light for so long all but vanished. The fog cleared. The universe, opaque since its beginning, became transparent. And in that instant, the light that had been trapped for hundreds of thousands of years poured out in every direction, free at last to travel, and it has been traveling ever since. That light did not fade or stop. It is still crossing the universe right now, stretched and cooled by all the expansion since, arriving at us from every direction of the sky as a faint whisper of microwaves. It is the oldest light there is, the single most distant thing any eye or instrument can ever see, because there is simply nothing older to look at. Before this moment, the universe was opaque, so no light from any earlier time can reach us. This is the wall, the farthest back the eye of any telescope can ever look. Every image we have of the infant universe is an image of this one surface. The moment the fog cleared, the first light set free. There is something that unsettles me about what that light actually shows us. When we map that ancient light across the whole sky, it is almost perfectly smooth, the same temperature in every direction to within a hair, and that smoothness is a problem, not a comfort. Regions on opposite sides of the sky, so far apart that light could never have crossed between them in the entire age of the universe, somehow arrived at exactly the same temperature. They could never have touched, never traded heat, never balanced out, and yet they match. How does a universe come out so evenly the same in places that have never once been in contact? It is the fingerprint left by that earliest ballooning we followed near the start, the stretching that took a single tiny patch, already uniform, and blew it up to fill the whole sky. But the smoothness is not perfect, and the imperfections are the most important part of the whole picture. Printed into that ancient light are faint patches, slightly warmer and slightly cooler, differing by only a few parts in 100,000, the tiniest unevenness imaginable. Those specks are the seeds. They are the stretched quantum flickers, now made visible, the map of where matter was a hair denser and a hair thinner at the moment the light broke free. Every galaxy, every cluster, every structure that would ever form is written there in faint, warm, and cool patches, a blueprint of everything, printed at the instant the universe turned clear. The oldest light carries the plan for all the structure that had not yet been built. And yet, at that moment, none of it was built. The universe went transparent, and what it revealed was almost nothing at all. No stars, no galaxies, no light from any burning thing. Only a vast, dark, thinning fog of hydrogen and helium, faintly clumped, drifting in the dark, cooling toward black. The great flash of released light would redden and dim, and after it the universe fell into a long darkness with no new light to replace it, nothing yet massive enough to ignite, just the seeds, waiting in the dark, and gravity beginning its slow work on them. But gravity working on that thin gas alone could never have built galaxies fast enough to match what we see. The ordinary matter was too sparse, too smooth, too slow. Something else had to be pulling, something already gathered, something that had been shaping the darkness long before the light ever broke free. What was already there in the dark, pulling the matter together before the first atom had even formed. Something was already gathered in the dark before the first atom formed, and we can prove it was not made of the same stuff we are. The problem is a matter of timing. When the light broke free, the ordinary matter, the hydrogen and helium, was spread almost perfectly smooth, its densest patches only a few parts in 100,000 above the rest. Gravity does build structure from unevenness like that, pulling the denser regions denser still, but it is slow. And starting from unevenness, that faint gravity acting on ordinary matter alone would still be working today. It could not possibly have assembled full galaxies in the few 100 million years it actually took. The galaxies formed too fast. Something gave gravity a head start. For hundreds of thousands of years, the ordinary matter was locked to the light, and the light's pressure fought every attempt gravity made to gather it, blowing dense regions back apart as sound waves, the ringing we followed before. As long as matter was chained to light, it could not clump. The light kept smoothing it out. So ordinary matter was forbidden from gathering into anything until the moment the light let go, and only then, starting from near perfect smoothness, could it finally begin. That late start is the whole trouble. Ordinary matter was held at the starting line until recombination, and from that late a start, it could never have caught up to what we see. So the galaxies we observe are impossible, unless something else was gathering all along, something the light did not press on. Something that ignored the light completely, that felt no pressure from it, that was free to start clumping under gravity long before recombination while ordinary matter was still pinned smooth. That something would have had a head start of hundreds of thousands of years, gathering into dense clumps in the dark, building deep gravitational wells while the ordinary matter was still locked flat against the light. And when the light finally released the ordinary matter, that matter would not have faced the slow task of gathering from scratch. It would have fallen into wells that were already there, already deep, waiting. This is the case for dark matter, and notice how it is built. We did not go looking for an exotic substance because it seemed exciting. We were forced toward it by a contradiction, the galaxies that formed far too quickly for ordinary matter to explain. Something had to be gathering before the light broke free, and ordinary matter provably could not, because it was welded to that light. So there must be another kind of matter, one that does not interact with light at all, invisible not by being hidden but by being genuinely untouched by light, feeling only gravity. Matter that gives off no light, absorbs none, reflects none, and simply falls together under its own weight in the dark. And this invisible matter left its fingerprints on the very light we just watched break free. The ordinary matter, chained to the light, was ringing, compressing and rebounding as sound waves, and those waves left the faint, warm, and cool patches printed in the oldest light. The dark matter was not ringing. It felt no light pressure, so it did not bounce. It just sat in its gathering clumps, pulling. And its pull changed the way the ordinary matter rang, deepening some compressions and not others, leaving a specific pattern in the sizes of those warm and cool patches. When we measure that pattern in detail, it only fits if most of the matter in the early universe was this invisible kind, outweighing the ordinary matter several times over. The ancient light itself tells us the dark matter was there, and roughly how much. I find it steadying rather than unsettling that the invisible thing shows up in so many separate accountings. The speeds at which stars orbit within galaxies, far too fast for the visible matter to hold them, need it. The way galaxies move within clusters needs it. The bending of light around massive structures needs it. The pattern in the oldest light needs it. The very existence of galaxies this early needs it. These are independent measurements from different eras and different methods, and they do not merely allow dark matter. They each demand it, and they demand about the same amount. When that many separate roads lead to the same invisible thing, the thing is hard to dismiss as a mistake. We cannot say what it is made of, and that gap is real. But that it is there, we know from too many directions to doubt. What we do not know sits right alongside what we do, and honesty means holding both. We know dark matter's gravity shaped the early universe, seeded the wells that galaxies fell into, and outweighs ordinary matter by several times. We do not know what particle it is, despite decades of sensitive experiments built to catch one drifting through. None has been caught. The stuff that outweighs everything we are made of, that built the scaffolding of every galaxy, passes through our most careful detectors without a trace, exactly as it passed through the early universe untouched by light. It is not a small thing to admit that most of the matter in the cosmos is of a kind we have never once held still long enough to identify. So the structure of the universe was built on an invisible frame. The dark matter gathered first, in the dark, before atoms, and drew the ordinary matter into the wells it had already dug. The hydrogen and helium flowed downhill into those wells, grew dense enough to collapse, and lit the first stars, hundreds of millions of years after the light broke free. Galaxies formed along the frame the dark matter laid, strung out across a vast web of invisible mass. Everything we can see is a lit tracing of a structure we cannot see, ordinary matter outlining the shape of the dark matter that gathered it. The visible universe is the smaller part, decorating a scaffold built by the larger, unseen part. And the invisible matter is only one of the two great unknowns the universe was hiding. Dark matter shapes how structure gathers, pulling inward, building the frame. But that sealed term does the opposite. It pushes. For billions of years it did nothing anyone could notice, sitting quietly in the equation while gravity ran the show. And then, long after the galaxies had formed, it woke up and began to win. And it is winning right now, faster every day. What is the thing that has started to pull the entire universe apart, and why did it wait so long to begin? In the 1990s, two teams set out to measure how fast the expansion of the universe was slowing down. Everyone expected it to be slowing. The universe is full of matter. Matter pulls inward through gravity, and all that mutual pull should be acting as a brake on the expansion, easing it gently down over cosmic time. The only real question seemed to be whether the brake was strong enough to someday stop the expansion entirely. They measured carefully, using exploding stars in distant galaxies as markers, and the answer came back with the sign flipped. The expansion was not slowing at all, it was speeding up. To trust that, you have to know why those exploding stars are such reliable markers. A certain kind of stellar explosion always detonates at nearly the same true brightness, because it happens when a dead star crosses a precise mass threshold and tears itself apart. Every one of these explosions is very close to identical in the amount of light it releases. So they work as standard markers. If you know how bright the explosion truly is, and you measure how bright it looks from here, the difference tells you exactly how far away it is. A faint one is distant, a bright one is near, with little ambiguity. Measure enough of them at different distances, and you can reconstruct how the expansion behaved across billions of years, reading the history of cosmic growth in the brightness of dying stars. What that history revealed is that the expansion has two chapters. For the first several billion years, the expansion was indeed slowing, exactly as everyone expected, the gravity of all that matter acting as a brake. But then, a few billion years ago, the slowing stopped and reversed. The expansion began to accelerate, and it has been accelerating ever since. Faster and faster, the brake somehow turned into an engine. Something switched the universe from coasting to a brake to pressing on an accelerator, and it did so at a particular time in cosmic history, not at the beginning, but well into the universe's middle age. This is where the sealed term in the master equation finally opens. That equation, the one tying the expansion to how much stuff the universe contains, had a piece we set aside near the start of the night, a term that behaves unlike matter in every way. Matter thins out as the universe expands, spread ever more sparsely through a growing volume, so its inward pull weakens over time. This other term does not thin out. It is a property of space itself, so every new stretch of space that expansion creates comes with the same amount of it, undiluted. As the universe grows, matter's inward pull keeps fading, while this term holds perfectly steady, and a steady push set against a fading pull must eventually win. That is why the two chapters exist, and why the turn came when it did. Early on, the universe was smaller, and its matter was packed more densely, so gravity's inward pull was strong enough to overpower the steady push and keep the expansion slowing. But every year the universe expanded, the matter thinned and its pull weakened, while the push held its ground. There had to come a crossover, a moment when the fading pull dropped below the steady push, and after that moment, the push would dominate and the expansion would accelerate. That crossover happened a few billion years ago. The universe did not change its rules at that moment. It simply diluted its matter far enough that a push which had been there all along finally came out ahead. We call the thing behind that push dark energy. It is not dark in the way dark matter is. It is not a substance gathered in clumps. It appears to be a property of empty space, a faint push built into the vacuum, present in every cubic inch of nothing, and the more nothing there is, the more of it there is. It is now the largest single component of the universe by far, outweighing all the matter, ordinary and dark together, making up around 7/10 of everything. The dominant feature of the cosmos is a push we cannot explain, woven into space itself. We named it so we could talk about it. The name does not mean we understand it. A push built into empty space, undiluting, driving the universe to expand faster and faster, is not a new character in this account. We met it near the beginning. The earliest ballooning, the stretching that took a speck smaller than a proton and blew it up to seed the whole sky, was driven by exactly this kind of thing. Energy stored in space itself, pushing space to expand at a runaway pace. The universe has done this before, violently, in its first fraction of a second. What is happening now is the same phenomenon, unimaginably gentler, playing out over billions of years instead of an instant. The beginning and the present rhyme, both of them ruled by a push hidden in the vacuum. When we try to calculate how much push empty space should contain, using our best understanding of the vacuum and the restless quantum activity within it, we get a number, and that number is catastrophically wrong. It is too large, not by a little, but by a factor so enormous, It is often called the worst prediction in the history of physics, our theory overshooting the measured push by a margin with more zeros than the situation can bear. Something is holding the real push down to the faint value we observe, almost but not quite to zero, and we have no accepted idea what. The dark energy is not just unexplained. Our one attempt to explain it fails more spectacularly than almost anything else we have ever tried to calculate. So the universe we live in is ruled, in the end, by two things we cannot name: an invisible matter that built every structure, and an invisible push now pulling those structures ever farther apart, and together they are most of everything, while all the matter we can see and touch and are made of is a thin, bright minority striding on top. We have traced the whole story, from the wall where physics fails, through the freezings and the annihilation and the first light, and we have arrived here. At a present, the universe hands us mostly in the dark. But there is one place where every chapter of this story is still written plainly, still running, still warm to the touch. Not out in the distant sky, but here, in the room, in the body lying still in it. How much of everything we have followed tonight is happening right now, inside you? We have moved through nearly the whole history of the universe tonight, and if you laid it all out as a map, the center would be drawn in hard ink and the edges would fade to faint pencil. That fading is not a flaw in the map. It is the map being honest about itself. So let me walk the map from its solid center outward and mark where the ink thins. That the universe is expanding, we see directly in the light of galaxies. That it was once a dense fireball, we read in the faint bath of ancient light soaking the sky. That it forged its helium in the first few minutes, we confirm by finding that same quarter measure of helium everywhere, in gas that no star has ever touched. These are not one clue leaning on another. They are separate roads, walked by different people with different instruments, all arriving at the same place. The hot, dense beginning is as solid as anything in science, as firmly established as the ground you would trust to hold your weight. Just outside that center sit the things we have not only inferred but rebuilt with our own hands. The merging of two forces into one at high energy, we did not merely deduce from the early universe. We reached the energy in a machine and watched the two forces become one, exactly as predicted. The searing plasma of unbound quarks that filled the universe before protons existed, we have recreated in miniature, colliding matter hard enough to melt it back into that state for a fleeting instant. The field that grants particles their mass, we found the trace of it, caught the signature of the thing switching on. These parts of the story are not history we are guessing at. They are physics we have made happen, again and again, and can make. The stretching that smoothed the universe and seeded its structure explains a great deal, and it fits what we measure with startling success. The pattern of warm and cool patches in the oldest light matches what that stretching predicts, closely enough that most who study it take it seriously. But fitting the evidence is not the same as being caught in the act. There is one clean fingerprint the stretching should have left, a particular faint twist woven into the oldest light by ripples in space itself from that violent first instant. We have looked for that twist hard, and we have not yet found it. So the earliest expansion sits in an honest middle place, strong, well-supported, and still not sealed. It may be exactly right, and it may need mending, and we do not yet get to say which. Beyond that, the map holds things we know are there and cannot explain at all. The invisible matter that built every structure we know exists from too many directions to dismiss, and we have no idea what it is made of, despite decades of patient searching for a single particle of it. The push, now driving the universe apart, we have measured cleanly, and our one attempt to calculate its strength fails more badly than almost any prediction we have ever made. The tilt that let matter survive over antimatter, we know happened, and the lopsidedness we can measure in the laboratory falls far short of explaining it. These are not gaps at the ragged edge of the story. They are holes near its heart, 3 of them, each one a thing that shaped everything and still has no name we can give it. There are 2 good ways to measure how fast the universe is expanding. One reads the rate from the oldest light, the early universe telling us how fast it should be growing. The other measures the rate directly, here and now, using nearby exploding stars as markers. These 2 methods should give the same number. They do not. They disagree by more than the uncertainty in either one, a gap that has stubbornly refused to close as the measurements have grown sharper. Nobody yet knows whether this is a subtle mistake hiding in one of the methods or a genuine crack in the whole picture, a sign that something in our account of the universe is incomplete in a way we have not yet grasped. It is an open wound in cosmology, and it is being argued over as we speak. If I have done one thing right tonight, I would want it to be the edges of this map more than its center. It is easy to tell the parts we are sure of with confidence, and the confidence is earned. The harder honesty is to hold up the faint pencil at the edges and not quietly ink it in, not let a beautiful idea that fits the evidence slide into sounding like a proven fact. The universe does not owe us a story that is finished, and the story we have is not finished. It is a map with a bright, solid center and real blank spaces near the rim, and the blank spaces are not failures. They are where the work still is. And past the outermost edge lies the wall we met near the beginning, the one place the map simply stops. Before that first unimaginably brief instant, our theories return not faint answers but no answers, because the 2 we would need cannot work together there. We do not know what the universe was doing before that wall. We do not know whether time itself had a starting edge, or whether the question of what came before is a real question, or only a string of words that stops meaning anything past a certain point, the way asking what lies north of the northernmost point of the earth stops meaning anything. That is the truthful end of the outward map. Not a mystery we have half solved, but a boundary where our questions themselves give out. So the map fades to blank at both ends, at the wall behind the beginning and at the dark things ruling the present, and yet almost everything between those edges is drawn in solid ink. It is a strange and honest picture, mostly known, framed on both sides by the unknown. And there is one place where the solid, known middle of it is not a distant record at all, but a living process still running, still warm, close enough to feel. Every freezing, every threshold, every ancient number we have followed across the whole history of the universe is present, right now, in the one place we have not yet looked. In the body lying here in the dark, listening. Everything we followed tonight is in the room with you, and most of it is inside your body, running right now. We went to the wall where physics fails, out to the invisible things ruling the present, across 14 billion years of freezings and thresholds, and all of it came home to the same place, because you are made of the leftovers of every step. Not as a figure of speech, the actual physics, the same equations, are operating in you as you lie here in the dark. Start with the hydrogen. Most of the hydrogen in your body, in the water that makes up most of you, has not been changed in any fundamental way since the first few minutes after the beginning. It was not made in a star. It was made then, in that brief window when the light finally dimmed enough for the first nuclei to hold, before the broken rungs in the ladder stopped the building. The stars came later and made the heavier things, the carbon and oxygen and iron. But the plain hydrogen was already there, forged in the opening minutes, and never remade. The water in you is carrying nuclei almost as old as time, unchanged since the universe was 3 minutes into its life. Now, feel your own weight, the press of your body against the bed. Nearly all of that weight we followed to its source. It is not the heft of solid stuff. It is energy, the straining of the strong force locked inside every proton and neutron in every atom of you, bound in at that instant when the free quarks were caught and confined forever. The small remainder, the weight your particles carry as particles, comes from the field that switched on across all of space when the universe cooled past its threshold, the field still switched on in this room, still gripping you. The heaviness holding you against the mattress is two ancient freezings at once, bound energy from one, and the grip of a field from another, both of them set in the first slivers of a second, and both of them still holding you now. Feel the warmth of your own skin, the heat held under the blanket. That warmth is a temperature, a little over 300 Kelvin, and temperature is the one clock that ran the entire universe, the single number that decided, threshold by threshold, what froze into place and when. The same kind of reading that once stood at billions of degrees, hot enough to make matter out of light, has cooled, in you, to the gentle warmth of a living body under a blanket in the dark. It is the same quantity. The universe is just far colder now, and you are one of the warm places left in it. And the light, the oldest light in existence, set free the moment the fog cleared and the universe turned transparent, has been crossing space ever since, and it has never stopped arriving. It is arriving now. Hundreds of millions of those ancient photons are passing through your body every second, through the dark room, through you, the faint cooled glow of the annihilation that left you here, still washing over everything, still arriving from every direction at once. You are not separate from the early universe, watching it from far away across time. You are inside its light, right now, bathed in it as you breathe. So the whole story is not a thing that happened long ago and ended. It happened, and it left, in you, a standing record that is still running. The hydrogen from the first minutes. The bound energy from the confinement of quarks. The mass from a field that switched on and never switched off. The warmth that is the last cool echo of a temperature that once made matter from light. And the ancient glow, still pouring through you in the dark. Every one of these was a moment when a perfect balance failed by the smallest possible margin and left something behind instead of nothing. And you are what all those tiny failures added up to. The universe did not become empty. It became this, and you, lying here, are the proof. There is nothing you need to do with any of this. No lesson to carry, no larger point waiting at the end. Only that the thing you are made of is the same thing the whole sky is made of, forged in the same first minutes, cooling now toward the same long quiet, and that for this one stretch of cosmic time, improbably, some of that matter has gathered itself into something that can lie in the dark and wonder where it came from. That is what you are doing right now. It is enough. Thank you for spending this quiet hour here with me, following something so old and so strange all the way to its end. It means more than I can easily say that you chose to spend it this way, thinking about the beginning of everything as the night settles around you. Rest now. The light that has been traveling for 14 billion years will keep arriving while you sleep, and it will still be here in the morning. Good night.